Hello everyone, thanks for watching this video about the identification of entropy waves in partially premixed combustors. My name is Alexander Eder, I'm from Technical University of Munich, and this study was carried out together with Dharmaputra from ETH Zurich and my colleagues at TU Munich, Alex Garcia, Camilo Silva, and Professor Wolfgang Polifke. Let's first of all imagine this is our combustor. So we have a swirl stabilized flow. We have air coming from left to right, and we have the fuel coming from fuel injectors. And the fuel injectors impinge into the airflow, and air and fuel is mixed at that injector position. And this causes locally richer and leaner pockets of the air-fuel mixture, so equivalence ratio perturbations, which are convected with the mean flow towards the flame where this mixture is consumed by the flame. And when the flame sees richer and leaner pockets, it burns at different flame temperatures. And this burning at different flame temperatures causes perturbations in the entropy downstream of the flame. And these entropy perturbations, these entropy inhomogeneities, they are convected with the mean flow, similarly as the equivalence ratio perturbations upstream of the flame. And what happens, these entropy waves, they decay throughout the combustor, and if accelerated, they are converted to acoustic waves. And this conversion can cause two different things, which are fundamentally related. On the one hand, the downstream traveling acoustic waves, they can add to the overall engine noise, and the upstream traveling acoustic waves, they can further enhance thermoacoustic combustion instability. So therefore, it's crucial to understand the behavior of entropy waves and the response of entropy fluctuations to upstream flow perturbations. And this is what we did in that study. Therefore, I want to first of all give you a brief outline of this talk. So I want to give you more information about system identification, because that's the methodology what we use in analyzing the numerical data. And I want to focus on system identification when it comes to entropy waves. Subsequently, I will show you the thermoacoustic test rig, what we used for this study, and the numerical domain of that rig. Then I wanted to focus on the response of entropy waves, where we validate our numerical setup with experimental results. And finally, as I said, these entropy waves, they get decayed, or they decay throughout the combustor. I want to give you more insights about this dispersion of entropy waves in such a turbulent swirl stabilized combustor. So first of all, when we talk about entropy fluctuations, I wanted to give you a brief definition of what entropy fluctuations are and how they are measured. So entropy fluctuations or entropy waves are inhomogeneities in the burnt gases, in the burnt gas temperatures. And in order to quantify them, let's start with a Gibbs equation together with the ideal gas law. And when we now add also the assumption that we don't have large pressure fluctuations and we have a low Mach number flow, with these assumptions, we get the approximation that entropy waves can be described by temperature fluctuations. So entropy fluctuations are approximately temperature fluctuations. And the nice thing about that is that these temperature fluctuations can be measured experimentally, which was also done already in the past with thermocouples, OH-LIV, or also TD-LAS VMS. The latter one is the method of choice in this work. Now, knowing that entropy perturbations can be approximated by temperature perturbations, I wanted to tell you more about how to identify, how to determine the entropy response. And again, this is our configuration. And when we talk about entropy response, we can use entropy transfer functions. And in a partially premixed combustion system, which has choked fuel injection, which means that the impedance at the fuel injector is equal to 1, and there is no perturbation of the fuel mass flow, together with the assumption that the distance between the fuel injectors and the burner outlet is acoustically compact, we can describe a partially premixed combustion system as a single input, single output transfer function, as shown here. So with the input, the velocity perturbations at the burner outlet, and the output, the temperature fluctuations, and the transfer function is the entropy response. And this seems or might seem a bit counterintuitive that a partially premixed system where we have equivalence ratio perturbations, global equivalence ratio perturbations in the burner, that this can be described with a single input, single output, so a seesaw transfer function. But we have to say that in that case, the velocity perturbations and the equivalence ratio perturbations at the burner outlet are fully correlated, and therefore we can use the seesaw transfer function. And as I said, this entropy transfer function is the overall frequency response of entropy waves to upstream velocity perturbations, which are coherent to the temperature perturbations. We can make use of a slightly more complex setup, namely the following. We force both the air and the fuel and monitor then the velocity and the equivalence ratio perturbations at the burner outlet in order to get the information of both excitation mechanisms. So we get the information, the entropy response only due to equivalence ratio perturbations and the entropy response only due to velocity perturbations. And with that, we can describe the system as a multiple input, single output, so a meso system where we have as inputs equivalence ratio and velocity perturbations at the burner outlet, and as an output temperature fluctuations. And with that, we can describe the individual frequency responses of entropy waves to both kind of perturbations. And why we are doing all that, so why we want to identify entropy transfer functions, is because we can incorporate these entropy transfer functions in a low order thermoacoustic representation of our combustor, and then investigate the thermoacoustic stability of the system. This can be done with the seesaw transfer function showed in the slide before, but also with a more complex setup with this meso transfer function. However, in the present case, we only investigate this meso transfer function to get an insight into both excitation mechanisms. Following, I wanted to show you the test rig, what we used for this study. It's this test rig located at CUPS lab at ETH Zurich in the lab of Professor Nicolas Norey. So thanks at that point for this collaboration. And we're talking about the partially premixed turbulent world stabilized combustor, which is water cooled and air force cooled and has a methane hydrogen fuel blending. And specifically, our operating point has an equivalence ratio of 0.78, a thermal power of 43.7 kilowatts, and a hydrogen volume fraction of about 59%. And the schematic of that rig can be found here. It's focused from left to right. So we have adjustable boundaries in order to assure a thermoacoustically stable system. We have loudspeakers to force the air mass flow at distinct frequencies. We have an air plenum. We have a fuel supply, which ends in the burner with 8 fuel injection holes, which impinge into the airflow. We have microphones to modulate, to reconstruct the velocity fluctuations at the burner outlet using the multi-microphone method. And inside the combustor, so inside the combustion chamber downstream the flame, we have this TD-less VMS setup for generating temperature signals. And additionally, we have quartz windows for optical access. And the tricky part in measuring this temperature fluctuations is that we need a high temporal resolution, which is one of the reasons why there are not too many studies out about entropy fluctuations and entropy transfer function measurements. Let's now focus on the yellow part. This is what we investigated numerically. And we did a large eddy simulation with a tetrahedral mesh, more than 70 million cells. We used a fully compressible AVPP code, and we used a fully compressible solver in that case because we had very high Mach numbers in the fuel injectors. So as I said, they were choked, so unity Mach number. We used a sigma turbulent closure without wall functions because we are wall resolved. NSCBC boundary conditions where we tune the relaxation coefficients in order to assure a thermoacoustically stable domain, the thickened flame model for turbulence combustion interactions, an artificially reduced chemistry mechanism for our methane hydrogen fuel mixture, and a diffusion model which is capable of resolving differential diffusion by specifying a Lewis number individual to each species. And with these numerical and experimental setups, I wanted to go into the analysis of the results. So again, I want to give you more insights into how exactly we force the flow in experiments and in numerical simulation. As I already said, in the experiments, we have loudspeakers at distinct frequencies. We modulate the air mass flow and track the temperature fluctuations at the position of the laser measurements and reconstruct the velocity perturbations via the microphones. In the simulation, we impose at the inlet at the air inlet of our simulation domain a broadband signal which looks like the following in time and frequency domain. So a broadband signal which consists of all frequencies of interest with a high power spectral density. And we monitor then the velocity perturbations at the burner outlet and the temperature fluctuations at the combustor outlet, and can therefore compute this CISO transfer function of the entropy response, which can be shown here. So the black line is the result of our system identification fed with the data from the large eddy simulation. Together with a confidence interval of 95%. And what you can see is that the experimental results are within, or nearly in all frequencies within the confidence intervals. And in the gain, we can see an overall low-pass behavior due to the convective nature of entropy waves. And when you look into the phase, what we can interpret here is, or what the phase tells us, is especially the low frequency limit. This can be thought as a change in one quantity, resulting in a new steady state of the system. And that means if we increase the air mass flow, that corresponds to an increased amount of air available for combustion relative to the fuel, means an excess of air becomes more pronounced, and the burnt gas temperature reduces. And therefore, U prime and T prime are out of phase, and the low frequency limit, the phase of the entropy response, is pi or minus pi, so shifted by 2 pi. And this is the result for the CISO transfer function. And in the next step, I said we wanted to investigate both excitation mechanisms due to equivalence ratio and velocity perturbations. And therefore, we use only numerical simulation because the rig is not capable of forcing the fuel mass flow. But in the simulation, which is now already validated, we can impose 2 uncorrelated broadband signals, once at the air inlet and once at the fuel inlet, and then track the velocity and equivalence ratio perturbations at the burner outlet, which are now nearly fully uncorrelated, and the temperature fluctuations at the combustor outlet. And this leads to this entropy transfer functions, or to these entropy transfer functions. And first of all, concentrate maybe on the orange one. This is the entropy response due to equivalence ratio fluctuations. In blue, the entropy response due to velocity perturbations. And the dotted black line is the overall entropy response reconstructed from the individual components. And what you can see is that up to 180, 200 Hertz, the dominant mechanism is clearly the velocity. There is clearly the equivalence ratio perturbation, which also fits to previous studies in literature. And afterwards, we can see that both are very similar or have very similar contributions. However, the gain is already quite low. And since we have now investigated the CISO and the MESO entropy transfer function, so the response of the entropy, we now wanted finally to focus about the transport of entropy waves throughout the combustor. And this is again done numerically, because we have simply the chance to write out temperature fluctuations at various positions in the combustion chamber. On the left top, you see these 6 positions where we wrote out temperature fluctuations computed with the CISO approach, the corresponding entropy transfer functions, which are shown on the right. And what you can see is that from position 1 to position 6, so traveling through the combustor, the gain is decayed through the, towards position 6. However, the entropy waves are not completely suppressed. And this is contradictory to some studies in literature which say that entropy waves are not that important because they are fully decay throughout the combustor. There are other studies which say they are important, and what you can say with this technically relevant swirl stabilized turbulent combustor, that what we see in our configuration is that entropy waves are not completely suppressed. And in the phase, what we can see is the convective nature of the entropy wave, where we have the time delays, the various time delays between burner outlet and the corresponding positions, and therefore we have this linear shift in the phase. Having said that, I wanted to come to summarize this presentation. So what we did is we investigated a partially premixed combustor. First of all, I gave a bit more insight into the system identification methodology when it comes to entropy waves. I described the partially premixed combustor, the test rig, and the numerical domain, which we further used for identifying the response of entropy waves, where we validated the numerical results with experiments, and finally investigated the dispersion of entropy waves. And with that, I wanted to conclude my talk and say thank you to you for watching this video.